Okay, so can you go ahead and tell me what volume you found in number 17?
16,744.
All right, nice. So that same object is now going to be floating in water. And you ever noticed how when you put something into the full sink or the pool, the water level rises when you add the object? That's because the object is displacing water based on its own volume. If you put a 3-liter box under the water level, that's 3 liters of water that got pushed out of the way. So if the entire box was under the water, it would displace 16,000, etc. Amount of water. But only part of the box is under the water. We were told 1.2 meters are sticking out the top. Meters or feet? Okay. Now, I apologize, and the question, neither 17 nor 18 specified which of the measurements is the vertical height of the box. So I'm going to go ahead and just tell you that since we're assuming this is a box, we've got one really long side, one pretty long side, and if it's a box, usually the vertical side is the shortest one. So we're going to assume that that 1.2 meters is being taken off of the 13. So instead of the full volume with the 13 meters, 1.2 of those vertical meters are sticking out the top. So to find the volume under the water, you would do the first two numbers times 11.8 instead. And that will give you a new reduced volume. This is not the actual answer, I'm still not remember the actual answer. So once you find that new volume, which is at least 15,000, I remember that much.
Yeah.
That's completely the answer to number 18. That volume of water, that volume of box under the water is the volume of water the box would displace. 19 asks then, if this is the density of that water, what is the mass of that water? So we just use the density formula, multiply the volume by density, find mass. Also going to do that because we're going to be talking about it today. Good morning, Jarbo. Sorry, I didn't mean to ignore you. Sorry. That's okay. I've been late pretty much everything today. It's just okay. I've been saying, I was going to say it's been a weird day, but I've had weird days for the past week, month, year, 5 years. It be that way. You're fine. I was nearly late and I knew, so figure everyone knows. Any other questions about that one? Okay. Give you a paper clip. And that new assignment right there, this is information for both of you. Since we will meet next Wednesday, we won't meet next Friday because of that wellness day. So this is today. Next Friday, April 2nd, is one of those bonus days, so no class that day. We will meet on Wednesday, March 31st, where we'll continue. We're going to start the assignment today, the new assignment today. We're going to work on it Wednesday. Since we don't have class that day, I'm going to say that I'm going to make that this new assignment due April 7th for right now. And so we'll collect it on the Wednesday, answer any questions, and then move on to number 7, the actual homework 7. Now, up to this point, we've been doing a whole lot of review of previous math principles, formulas, order of operations, etc. The rest of the semester, we're going to start doing some physics, and I'm going to show you how this is all going to be useful in proper physics classes. And some of this might be retreading what we talked about on Wednesday. Sorry about that. But I'm going to make sure we look at some other problems in the assignment too. So, when one starts a physics class, one of the very first things we begin talking about, and that we will be talking about, is vectors. Have you heard the word vector before within your recollection? That is okay. This might seem like a strange question. Have you watched Despicable Me 1? Yeah. Okay. I only bring this up because it's like the one commonality, the one common point that all of my students have for this word. The villain of that movie was called Vector. Like that was his super villain name. And he pretty accurately said that the definition of a vector is an arrow with both magnitude and direction. And then there was something about a squid gun. But beneficially, that definition given is the correct one. In math and physics, we define a vector as a quantity that has a magnitude, but also specifies what direction that magnitude points in. This is different from a scalar quantity, which is only a magnitude with no direction. And when I say magnitude, that's just the highfalutin way of saying a number. Numbers are magnitudes. It's just a measure of how big whatever you measure is. So anytime, any number you've ever dealt with that doesn't specify upright, left, down, north, south, east, west, has been probably a scalar. Like normal numbers are scalars. Vectors, however, have to specify what direction the vector points in. It's an arrow, it is going somewhere. And you've been dealing with vectors your whole life. Some common examples include displacement, velocity, and acceleration. If you're moving in a direction, we note what direction that is. So, for example, you could write, I displace 10 miles north. I am driving or walking 16 meters per second in the positive x direction. And all of those carry some sort of directionality with them. North, we usually draw as up on the XY grid. This little symbol right here indicates positive x direction on an XY graph. So I'm going to be using these often enough to describe directions on a graph. So this is just notation for that. You can also do, hat Y underline to indicate the y-axis. Excuse me. And there are some other things that are always vectors, like force. You measure force in newtons, and if you're pushing on something, you have to push in a direction. So all throughout any physics classes you take, we're going to be talking about new things to measure if they're vectors or not, what we do with them. And if you look at the assignment, the first page and several of the questions besides that have graph sections on them, because Since vectors can be drawn as arrows, we are going to look at those formulas, draw by hand some graphs based on them to actually visualize the vector arrow. You don't need to use a graphing calculator for this. This is just taking a formula and plotting some data points by hand. There are some things that are typically scalars that can't have a direction attached to them. Common examples include time, because you can't have 1 hour up, and mass, because mass is just a measure of how much material is in something. That doesn't change whether you're on Earth or the moon. It's just a number. So all throughout physics, we'll be defining if a new variable is a vector or a scalar. If it's a vector, we can graph it, we can draw it with an arrow. And the three first vectors that we would be dealing with, and that we'll be showing a little bit of today, is these three: displacement, velocity, and acceleration. These three terms describe how everything moves, and we can use them to determine where something started, where it's going, when it's going to get there. And because we like to have formulas written in physics, those three concepts have several formulas between them, because these are the first three vectors that we commonly interact with, and these are the formulas that relate to these vectors. This department has taken to calling them the Fantastic Four, which is the thing that we've been doing here since before I was a student, because these are important, and we build on them to do pretty much everything. And the formulas on the first page of the assignment are actually variations of this third one. I advise you guys to go out to look at these, copy them down, begin looking at or continue working on the first page. I will be right back, because everyone has to go to the bathroom eventually, even the teacher. Okay, sorry about that. Now, I'll make these notes available to everyone, so if you want to refer back to them, they will be at your disposal. I want to look briefly at everything on the first page, how to graph those together, and what they might physically represent in physics context. The first three questions, I would call those linear displacement questions. All three of those formulas could be rewritten to say displacement final is equal to the person's velocity times time plus their initial location. And in that context, if you were to say graph this on a displacement versus time graph, time on the x-axis, displacement on the y, we could track where this person is on a specific axis as time goes past. And all three of the first ones can be described similarly. What differs between them all is simply slope and starting point. This particular formula here, if I was to generalize it, would be df equals velocity times time plus distance initial. We have our starting point, how fast we move away from that starting point, how long we are moving, and where we end up as a result. And so for those first three, what I recommend doing is to actually create a graph is just take the formula, plug a series of numbers in for x on the page, find those y values, and chart the x and y pairs, and then draw a line accordingly. I think the first one comes out to 2.3, 4.5. Something like that. The second one has an inverted slope but the same starting point. So it kind of forms an X. And the third one has the same slope as the second one but a different starting point. And I like drawing them on top of each other to show the differences, but you have three separate spaces if you want to put them all separately. I just want to show them real quick to kind of highlight the differences between them. The three formulas given for those examples are 1.2x, I'll rewrite these as it's shown on the page, y equals 1.2x plus 2.3, y equals negative 1.2x plus 2.3. Y equals negative 1.2x minus 3. Same numbers, but each time we are changing the direction of movement, and one time we are changing the starting point. So if these are three people walking three separate paths, two of them start at the same point, but then move in opposite directions. One of them starts at a different point, but moves in the same direction as person two. The second set of questions, 4 through 6, are the slightly trickier ones in that they're a little hard to draw and hard to visualize. These straight lines are good classic vector examples. They're literally lines, they literally point somewhere. But the next three, numbers 4 through 6, are parabolas. And while it might not look like a vector that points in a straight line, parabolas are made of vectors. So we showed this formula a moment ago. And this formula here describes describes location, where something ends up as a function of time based on, well, sometimes I prefer to write this as x final equals v initial times time plus 1/2 times acceleration times time squared plus x initial, which shows kind of the quadratic form of having three things on one side equal to something else. But that formula best represents the movement of an object as it is accelerating through space. And the easiest, most classic example of acceleration is falling. So a common use for this formula and for a parabola in our early physics work is going to be looking at the movement of a falling / thrown object. Because if you were to throw anything up and forwards at the same time, its trajectory forms a parabola due to the fact that it wants to move up and forwards, it wants to move that way, but the Earth is constantly pulling it down the entire time, changing its its y velocity. So the parabolas graphed on the assignment will not always be the same, because I know at least one of them points upwards, but mean similar things and can be interpreted in similar ways. And so all the parabola questions on the first page, they aren't written in this form, but they could be. They could be rewritten as a quadratic, which is the formula that forms this shape, and they could be interpreted as such. But rather than doing a quadratic equation, since what we need to do is graph them, my recommendation is determine each parabola's vertex. Vertex being the sort of lowest or highest point at which point the parabola then turns around. In the case of a thrown object, the vertex would be the point where it's at its highest and then starts rolling down. And for each graph on the assignment, for number 4, that vertex is going to be at coordinates 3, 4. I know this because when looking at the way the formula is written, if you plug in a 3 for x, then 3 minus 3 is 0, 0 squared is 0, 0 times 3 is 0. That leaves our answer as 4. So 3, 4 will be the vertex of this graph. And so 1, 2, 3, 1, 2, 3, 4. From there, my recommendation is taking this 3, the x number, add 0.5 to that 3, put it back in, see what you get. For this particular one, I got 4.75. So for x coordinate 3.5, I scroll back up to 4.75. Then you add 1 to that x coordinate, so I'm going to plug 4 into the formula, and that gives me 7. Plot the 4, 7, that goes right there. And then you want to check in the opposite direction. So 3 minus 2.5, 3 minus 0.5, we would put 2.5 in the formula. That also gave me 4.75. And similarly, if we put 2 in here, 3 minus 1, that gives me 7 again. I'm recommending this stretch of modification to the vertex, because if you were to put in +1, +2, and -1, -2, those last two numbers would be bigger than fit on a 10 on this particular graph scale, since each axis is only shown up to 10. And I did this intentionally so that everything would be visible on each one. So for this first graph, starting at the vertex and plotting additional data points out from there, just fill in the loose shape of the parabola, and that's it for the first one. These are the hardest ones. I find the parabolas to be trickier, so I want to talk more about those. The next two, you know their vertices. We've got -2, -2, and -4, -4. And calculator. Starting from -2, if I put in, let's see, -3, open parentheses. -1.5 plus 2 squared -2. That gives me at -1.5. That gives me -2.75. And that's -1. And it should scale the same way on the other side. And that would be the second parabola. Third one, I think the third one would actually point upwards, but same method. And again, the shape comes up pretty often. We've already dealt with it as a quadratic, less so than as a picture. Do you guys have any questions, or is there anything from the first page you'd like to look at in more detail? Okay. Now, I do want to apologize quickly. Going from page 1 to page 2, we skipped from problem 6 to problem 11 because MS Word hates me. Similarly, on the last page, we go 16, 17, 18, 18, 20, 21. So the one that should be 19 got relabeled to 18, which is only problematic because question 20 says, given the velocity you found in number 19, so-and-so and so-and-so, how does this compare to number 18? So I'd recommend going ahead and relabeling this one as 19, just to cut that off now. Okay. Now that is as much as I've covered across all my sections so far. So I'll leave it to you guys. We can start working on the next couple of vector problems, mainly how vectors add together. I'm also comfortable calling it here for the weekend. Any opinions? I think I might be inclined to at least show you one of the vector addition problems, just to go ahead and get that determined in your heads. Just very quickly now. If you look at page 2, number 11, we are asked to start adding vectors together. And vector addition gets tricky because say someone walks, 2 feet east and then 3 feet north. Now, if we were asked what is the total number of feet this person walked, we could say 5. If we were asked how far is the distance from here to here, the answer is not 5 anymore. The answer is a triangle. Have you guys worked with things like this before? Okay, cool. I never know how much of this is review for any given student. So, in order to add vectors together, it's recommended that you draw them out physically, tip to tail, and divide them up into triangles, and you can only add or subtract components in the same axis together. So, as an example, let's say we wanted to add this vector to this vector. If someone walked this trajectory, the distance from start to finish would be this. In order to actually get that number, each triangle is going to need to be broken down into its X and Y components. And then the X's added together and the Y's added together, or in this case subtracted since they point in opposite directions. And those two things summed together will create a triangle for the final sum vector. So most of the questions from number 11 onwards will employ this method. Go ahead. My request is for you to finish the first page over the weekend. Begin working, or at least begin processing the next couple of pages, and we'll pick up with how to do those next Wednesday. You guys need anything for the break? Okay. Okay, it's Friday. Please go enjoy yourself as much as one can. Rainy and gray. Stay healthy, stay safe, stay untornadoed.